Great. Hello, everybody, and welcome to Everything You Need to Know About Developing Classification Solutions webinar. It's, I think, number 19 in our series of webinars. My name is Neil Gallagher, and I'll be taking the first portion of this webinar, and then Donald gets to do all the hard parts. I appreciate Donald Sullivan agreeing to do that. And Barry had a conflict this morning, and hopefully he'll be able to come in at the very tail end and show a couple slides at the end of the webinar. Our webinar is being recorded, and it's going to be posted here at Resources Webinars as soon as we can, and Barry will send out a note about when that's available. Scott Koch is kind enough to act as moderator, and we'll ask that people stay muted during the webinar and post questions into the chat. And most of the questions will be related from the moderator to the speaker or actually answered directly in the chat. We have quite a few folks from Eigenvector here today that can answer all the questions. In the outline, I'll be talking about preparation and setting up classes for the classification to be used in our methods. Then I'll do an overview of the available classification methods where I'll show some specific tools, but most of the broad outline will show just a very brief conversation about each of the methods available. Donald will be talking about interpreting results and optimizing models, and then we'll present the hierarchical models, and that's Barry should be here back to talk about that. So under resources, we talked about the webinar resources. There's quite a few tools that you can look at, or recordings you can look at, including getting started with using the tools, how to import data, principal components analysis, which is an extremely important exploratory analysis tool that you would be the first thing that you use in all of your classifications. Partial least squares, cross-validation, and a whole bunch more. There's also recorded courses under training. So if you're not getting everything answered here today, those are some resources for you. The things we're going to be talking about under the classification is we're going to be talking about, for example, the SIMCA method, soft independent method modeling of by or of class analogy. That'll be the first one. We'll be talking about KNN right after that. And then I'm going to be talking about PLSDA, and I'll show some of the details and how the model building step works with PLSDA. Then I'll do an SVMDA and to switch over and show you how to change methods and how everything kind of works together. Everything's kind of under a similar metaphor. Donald will take over at the ANN and the XG boost part and the logistic regression. So data set, I'm going to work with a TOF-SIMS, time of flight, secondary ion mass spec data set that is based on a set of measurements on these polymers where the chain length or backbone length has been changed. And the backbone is given over here, and it's changed from 2, 4, 6, and 8 CH2 units. And as we've also got a side chain length that's being changed. And we're measuring our mass spec, and the question is, well, can we classify those? Can we identify which one it is? And thanks to Anna Blue for the data set. So let me go ahead and escape here, and I'm going to go to my PLS workspace browser. This is the solo browser. I've got my Arrelate data set already loaded up. I'm going to double click on that data set, and I'm going to show you where the classification information is. You'll notice that I've clicked on the row labels to bring up the row or sample information. I've got my labels down the left-hand side showing what the backbone and side chain is. And then I've got my class information on the right-hand side here. And in this case, I've got, for example, length 2 and length 4 of the backbone. This is my class set backbone. And I also have side chain information. And so I've got 2, 4, 6, and you'll notice that these are in triplicate. And I can also do the combination of the backbone, and side combo. I'll go back to the backbone. I'll right click on the class information to show you that there are lots of places where you can modify this class information. You can even take CSV files or copy and paste from Excel into the class information to create new classes. So I can create a new class if I wanted to, but I can also get into my class information here in the lookup table. Class length, for example, I could change that name to be more descriptive if I wanted to. So this is the place where you're going to save and notify each of the samples as to what class they are. Class 0, if I right click again and show this at a lookup table, class 0 is actually a special class that's not used. It's kind of like an unknown class, whereas anything that has a positive integer is considered a class that can be used for classification. Okay, let's talk about some of the classification techniques now. Oops, laser pointer. So SIMCA, Soft Independent Method Class Analogy Classification, is a case where each class that we've got is considered a PCA model. So for example, if I've got class 1 over here, I can draw my Hotelling t-squared ellipse around it, and then I've got my Q is perpendicular to it. My Q residuals are perpendicular. And then if I've got new samples that come in, like this guy, he looks like he's inside this ellipse for this class and inside the Q residuals, so he belongs to class 1. So that's just basic PCA modeling. And what SIMCA will do is take a PCA model for each class and then assemble a model as a series or collection of PCA models, and then look at these statistics relative to the distance from the model based on Q and T squared. So in this case, this guy's outside both of my classes. I got class 2 down here as a 1 PC model. This one is a 2 PC model. You can see because it's an ellipse. And this guy's outside both, so he doesn't belong to either of them. But on the bottom here, I've got an example where this particular unknown belongs to both classes. And so that's a possible. It can belong to one, none, or more than one. In K-nearest neighbor, or KNN classification, we get unknowns being classed based on how close they are, and we use a voting method. So here's an unknown down here, this little square. I've got class on the right-hand side in X's, and pluses is another class over here. And we'll do make distance measures. I'll measure the distance to all the points in this class here and all the points in this class here. And I find the 2 that are closest to this particular sample and say that it belongs to that one because it has 2 and this one only 1. Well, of course, my K here is 3, could be different. It could be bigger. And we typically use an odd number so that we can make a vote count. This particular method is reasonably good with nonlinear data. In PLSDA, we try a different way. Let's say that I've got 2 classes, the red one and the green one. The idea is that I'm going to build a PLS, partial least squares model, that finds a vector that goes from this class to that class, and I'm going to draw a threshold at some point in between these classes that provides my best classification. Well, the Y block is going to be a set of logicals, dummy variables, zeros or ones. In some cases, people use a -1 and a +1 for the classes. And then we just develop our typical partial least squares model. And we can do that here in just a second. And we'll develop a threshold between 0 and 1 to say which class you belong to. And there's also everything you need to know about performing PLSDA plus an addendum to that. So let me grab my data here and show an example of a PLSDA modeling approach. So I'm going to grab my data from my workspace and drag it over to my classification PLSDA and drop it on there. Starts up my analysis window, and this is our common interface for developing models. And if I mouse over, you can see I've got my data loaded. It's 47 samples by 433 mass channels. And I can click on my model builder here, constructor, that allows me to select class groups. So I click on the green crooked arrow here, and it brings up this DA class groups. Now, if I use the default, what it's going to do is it's going to select all of them and say, I'm going to model each one independently. So each of those classes are going to be modeled independently. Now I can remove them, and I can also group them. So if I did a PCA and found that 2 and 4 seem to split together and 6 and 8 split together, I can model those as 2 separate groups and have 2 separate classes. You'll notice that I'm working with the backbone class. I could use also the sidechain class. Click OK to use this classification set of groups. I click on the cross-validation method. So I'll set mine to just something simple, Venetian blinds, and I'll have 3 samples per blind because we had 3 replicates. I'll say OK. Close most of the defaults. There's a webinar on cross-validation. I can click the gears or the model button to start creating my model. And so there I went through all my cross-validations and developed a whole bunch of PLS-DA models that I can evaluate. And I look at, by clicking on this button here, looks like an eigenvalue distribution, but this has my cross-validation information. In this case, I've got my cross-validation error average. Typically in PLS, remember that we look at root mean square error cross-validation. For example, this one here. That's really not what's of interest in this particular approach. Instead, what we really want to look at is the classification error. And you'll notice the classification error for cross-validation starts out high and drops and finds a minimum at about 4 latent variables. I can also control-click on this bottom one to show that this is my calibration. And so calibration is not the most interesting thing. It's our cross-validation that we're really interested in. I can also look at scores just like we do in anything else. And you'll notice that I've got my classes in colors, and I can click on each of these classes. So there's the length 2 class. Here's my discrimination line being there. There's my class length 4, my length 6, and my length 8. And in this case, it looks like I've got a pretty darn good model because my cross-validation, I'm plotting my cross-validation predictions relative to this discrimination line, and I can split my 2 classes just fine. Now in SVM, we do something a little bit differently. Somewhat similar in that I'm trying to find a boundary between classes. I'm trying to find a best boundary between classes. But the question is how do I find this boundary? And in SVM, what I'm going to do is I'm going to try to find the 2 points on the outside out here that separate these 2 classes the best. So 2 points over here and 1 point over here. That I'm selecting 3 vectors or support vectors that split these classes the best possible in a linear discriminant way. We can also do this in a non-linear method. And so if I look at my error-late problem, I can change this now to a SVM classification technique by clicking on that very simply, clear my model. And there are other meta-parameters, but all the modeling approach is very similar. I'll change my class groups. Remember we had group 2 and 4 were modeled together before. I'll just use the default. I can just close this, it'll use the default, or I can click default and use that and say OK. And I'll start my SVM model, and I'm using a parallel processor here, so it goes very fast. I can look at my optimal model, and you'll notice that it optimized my parameters. It went through a set of parameter spaces, the gamma and cost function. Donald, who's going to be speaking shortly, is the SVM god, if you will. And so our model was picked up here with that set of parameters. We can also look at our scores. There's my measured, class measured, but I really want to look at my cross-validated predicted. And you'll notice that length 2 is predicted perfectly in cross-validation in this model. Length 4 looks like it's great, except for I've got 3 of them are classes, class 3. Class 3, oh, it looks like it's all the way up here. It looks like it's going to be modeled with length 8, so they look pretty similar. So maybe I might want to model those two as a group, split those off in a hierarchical sense, and then try to split them later. Or most of my pre-processing, or all my pre-processing here, I use my default, which was just mean centering. And we could play with mean centering, scaling, and all of that. And there's a webinar on pre-processing as well. How are we doing on questions over there, guys?
Well, there are no questions yet, so I guess we're doing all right.
Excellent. Okay, Donald.
Thanks, Neil. If you actually back up to the previous slide, there's one more thing I'd just mention about that. So in discussing classification, this sort of simple example of two classes and how we build a model to separate the two classes and predict samples belonging to one or the other. It's, this is the simplest idea, that you draw a margin between the two classes and initially just a linear boundary. In this case, often the two classes may overlap, so it's not possible, they're not linearly separable. And in that case, you would want to allow for the possibility of there being a sample inside that margin. So to do that, you solve the same problem of optimizing to find the widest margin, but associating a penalty with any samples that happen to fall within the margin. So that introduces a hyperparameter to the SVM, and that would be a cost parameter, which actually is called cost. It's a C parameter. So for linear SVM classification, that's really just the one parameter that you would have, the cost parameter. Almost always, it's simpler to have a non-linear boundary so that you allow it to curve, and it can, many binary situations, two classes will be separable if you can have a smoothly curving boundary going between them. And to do that, we use what's called a different kernel, and the common one is called a Gaussian radial basis function. And there is also a parameter associated with that, the gamma parameter, which it basically determines how curved it can become. If it's the way it's defined, if it's a very small value, it is effectively linear. But if you make it large, then it can be very curvy, very convoluted. And that's the advantage, but also maybe the disadvantage of these nonlinear methods, that you have multiple hyperparameters. So the question is, how do you pick which one to use? And in the model that Neil just built, with SVM, it actually searches over parameter ranges for each of, in that case, the cost parameter and the gamma parameter. It will search over ranges that are set by default, but which you can edit, and using cross-validation, pick the best parameter pair in this case. And that will be what will be used for building the model and for doing predictions.
We had a question in the chat. If two classes overlap in a model, how would you describe their similarity or degree of similarity?
Well,
Donald's going to talk about probabilities here, not too long.
Yeah, we will actually talk just after we go through a quick overview of the different methods. The next, I have about 3 more to go through. Then we will talk about like the summarizing of the classification, and that would be with the confusion matrix, where it's more relating to how well your model can predict the classes than exactly describing the class's similarity. So within these methods, we're not actually essentially describing like their probably their distribution, spatial distribution, but more just focusing on trying to predict class. So yeah, the question about the degree of similarity, it really just reflected here by whether you're able to separate the classes and predict the classes well or not.
There was another question relating to the example that Neil did, is how well would Simca have done if you'd tried all 4 separate classes?
Neil, go ahead with that.
Yeah, it's not too bad. That particular problem in Simca really works reasonably well with it. I know that some people don't like Simca that much, but I do because it's very intuitive and easy to interpret. So yeah, it's not too bad for that problem.
Great. And all of these methods that we're talking about here, we'll usually describe when we're introducing them. We'll just describe them in terms of a 2-class problem, but they all can be extended to multi-class. Okay, next slide then, Neil. Okay, so the support vector machine has been in the software for quite a while now. After that, we added the neural networks for both regression and classification. In classification, it's quite similar. The whole idea behind a neural network is that it's a kind of a nonlinear combination of inputs. So in the little diagram on the right, it's a schematic for a very simple, sort of the almost simplest neural network that you could have. At the left, the red points indicate the variables for a single sample. So in this case, there are the X data has 3 variables, and we take for a single sample, you take those values and combine them. Each of those arrows has a weight associated with it. So basically, you're taking a kind of a weighted combination of the inputs, and that gives you a value at each of the blue nodes. So after you've taken that sample, its 3 variable values, advanced to what we call the first hidden layer, you now have basically 2 numbers, and they are combined again, going to the output layer with weights associated with each of those connecting arrows to produce a final output. Now, in addition to that kind of weighted combination of the inputs, there is a nonlinear, what we call an activation function, that converts the weighted combination coming into the hidden layer node and maps it. It's usually something like a sigmoid or a tanh function. So it will map it into sort of the range of -1 to 1 or 0 to 1. But it's a nonlinear transformation, and that's what gives these neural networks their flexibility and ability to deal with nonlinear data. So as far as, yeah, that's a very simple one. In our software, we have, it's I guess limited, but it's also somewhat of an advantage really, that you can have 1 or 2 hidden layers and as many nodes as you want. We have 2 implementations of ANN. One of them is called the BPN, which is this stands for what this kind of a network is called, the forward feed back propagation error correcting network. And that's the part that I didn't mention there, that once you pass a sample's data, the three variables in this case, through to the end, then you can compare it with what the calibration data, what the known outputs should have been, your Y values, and get an error. Then, if you know what that error is, you can try to adjust the weights of those connecting arrows to such that if you pass the data through it again, that you would get a smaller error. And that idea has been around for a long time, but it was the realization that you could very efficiently modify those weights by doing and kind of propagating the error backwards to adjust the weights that led to the neural networks becoming very common in machine learning. Sorry, go ahead.
We had a question. Is the process from the input layer to the single hidden layer like a dimensional reduction step?
It would be actually that if you, for example, in this case, we have three variables and it kind of gets squeezed down to two variables. And of course, you could have more hidden layer nodes than you have input data variables. So in that case, it's sort of like an expansion, which is a little strange. There are some people do talk about, use that sort of idea of determining the complexity of the data by seeing how many nodes you need in a hidden layer, but it's not used very much because the overall focus is more on just getting a good neural network model with however many nodes you want. So kind of getting back to the idea of hyperparameters, as we were talking about with support vector machine, this is sort of the one of the issues with neural nets is to determine, what is the optimal architecture to use here? How many nodes should I have in the first hidden layer? And if I have a second hidden layer in there, how many nodes should I have in that? So as I said, we currently have two implementations, the BPN, which is this very simple forward feed back propagation error correcting model. And the other one is, and which is implemented in MATLAB code. The other one is the NCOG. And basically we allow you to build the same type of network, but using it's a different implementation. You would think that being the same architecture and kind of design, that they might produce identical results, but in practice, there's enough details within an ANN that, like in how the error is reduced, the solver mechanism, that they do perform differently. And the BPN method is we're very, very happy with the performance it gives. It often gives the best classification results. Its problem is that it doesn't scale well with the number of samples in your data set. So if you have a lot of samples or a lot of variables, like several hundreds or certainly over 1,000 of either samples or variables, it becomes very slow. The NCOG is a lot faster. And I should just mention that we will have two new implementations available with the next release, which are based on Python using the SK learn package and also TensorFlow. And those are much, much faster. So we're kind of excited about that.
I had another question. How many categorical variables can ANNDA handle?
Well, by categorical variables, there's no real limit on the number of variables on the input data. As I said, the ANN becomes slower to build if you have many, many variables, like over 1,000. And as far as the number of classes you can model, again, you can have as many output classes as you want. There'll be an output variable for each class. So, but as usual in any of these methods, performance, the classification ability will become more difficult to do as there are many classes. But there's no built-in limit.
It's kind of nice to use compression, for example, PCA, and just look at the scores ahead of time rather than having every variable.
Yeah. Thanks for mentioning that. That is something that with these classification methods that if you have many variables, the performance will become really poor. But we can use compression on the data, basically either PCA or PLS compression to convert the X data into scores, and you can decide how many principal component scores or PLS latent variables you want to use. So you could reduce, your 5,000 variable data set down to something manageable that still captures most of the variability in the X data. And that's available in the interface, so it's quite convenient to use. Okay, let's move along. The logistic, I actually click again because there was a build on this one more time. So logistic regression was actually the most recent method that we've added to the software, and it's a linear classifier, so that the separating boundary is linear. It's kind of a classic method, and that's why we added it and had been interested in it from our users. Again, the idea is to find a separating boundary between, in this case, two classes that best separates. And if you look at this, then anything that's on one side is class A or class B. But the thing about the logistic regression is that we associate a probability with the distance from the boundary. And basically the solving of the logistic regression model is finding these theta parameters, which kind of define the boundary line. In fact, in this simple example here of two-dimensional data, where X has just two variables, that line would be described by the theta naught plus theta 1x1 plus theta 2x2 equals 0. All the points on one side of the line, if you had a typical point, would be positive, or on the other side would be negative. Then this the logistic function is applied to that as described there, where you have the cursor showing how that's converted into a probability. So right on the line where that theta dot x is equal to 0, e to the 0 is 1, so that h of x becomes 1 over 2. So the probability of being class A is 0.5. But then as you move into the green side of the area, that will increase from, as you move away from the line, that will increase, but it will actually only increase to 1. It will not keep increasing beyond 1. In fact, it never actually attains 1. And that gives the probability of being that class. And this can be extended to multi-class as well, and in the implementation it does. Okay, next slide. A recent one that we added is, as I mentioned on the lower part of the slide there, is XGBoost. And that's a gradient boosted decision tree ensemble method. And the idea behind boosting of a classifier is that you take a collection of classifiers and combine them, and by combining them you actually will get a more powerful classifier. It's sort of the strength of many votes. And then a variety of those is called gradient boosting. Just basically the additional classifiers that you include are somehow modified based on the first one that you did. This modifies the second one, and so on. And the implementation that we used, this XGBoost, is one that is very popular, became very popular in some of these online data analysis competitions, where it often was used in the like the top entries. It's a very efficient package that we use. It's an open source one that I give the link to there, and you can get. It's a nice web page for describing that. So that's available as a classifier in the interface, and also has a regression version. Okay, next slide. Oh, and it's very kind of difficult to summarize in one slide, but this is sort of a very brief attempt. That in this case we take one of the parameters to XGBoost or any of these gradient boosted methods would be what is the maximum depth or complexity of each tree that you want to allow. And if you were going to allow very deep trees, then it's going to be more complex models. So you might want to limit it to 1 or 2. And in the end, that would sort of guard against over complex models and potentially overfitting. The other parameters that come into play here are well, the tree depth, the number of trees that you include in the ensemble. That's called a number of rounds of tree development. And there's also a parameter called eta, which is a learning rate, which basically says how much each subsequent tree that you add to the ensemble is going to influence the final solution. Okay, so let's go one advance slide. At this point, yeah, as I said, all of those are available in the interface. And actually, Neil, it might be a good idea just to pull up one of those. Let's say pull up the A and N, for example. Sorry, A and NDA. And click on the options icon. So just make sure that everybody sees what that is.
Yeah. Doesn't seem to change.
Oh, well, okay.
There it goes.
Yeah. So for all of these methods, if you click on that options icon, the second icon on the toolbar, you get to see all the options that you can change. And so this was this is A and N. Yeah. Okay. So this is A and NDA. There's the learn rate, learn cycles. Those are the main parameters here. Also below it, of course, for A and NDA, there's like the termination conditions that you might want to change what the terminal RMSE or RMSE rate are. And those are basically just, try different values and see how the results look. But the reason I wanted to show that was just that all of these methods, you would want to look at the options and take a look at the wiki page. We have a wiki page for each of these methods, which will explain what the options are and which ones are important, etc. Okay, you can go back to the slide. Thanks. So the thing with the classification is that it's often you have multiple classes, and it's a little not quite as easy as with regression problems where we have the root mean square error of prediction or cross validation, which is a very concise and convenient measure of how well the regression model is behaving. With classification, samples will be assigned to classes. There isn't really as convenient a summary of how well the model is doing. So in our software, there's two ways that you can look at the results. And one is sort of an overall view, which is through the confusion table or matrix. which we'll talk about in a second. And the other is by looking at the individual samples, predicted classes, etc. An important point that I think Neil mentioned already, that all of our classifiers are enabled to produce a probability for a sample belonging to each class. So that probability output is very convenient to have, both because it's useful, but also because it makes it easy to compare between methods, as opposed to having kind of different output for each method, whether it's based on like a threshold, and KNN was an example of that. So with KNN, you look for a test sample, you look at the K nearest neighbors and decide by a voting which of the K nearest neighbors and the classes of those K nearest neighbors, which has the most votes, if you will, and that would be the class you would assign to that. In the case of KNN, we actually converted that to a probability of belonging to each class, just based on how many votes were associated with each class for that sample. And we have a wiki page which describes how that sample classification is done for each method. So okay, let's move on to the next slide, which is talking about the confusion matrix. So probably, okay, I'll describe it first, and then we'll go look in the interface and just pull it up. But in classification, as I said, there's not one measure that summarizes completely how well the model is behaving. But for a two-class problem, the traditional way of viewing the results are to look at the true positives, the false, and the true negatives, and false positives and false negatives. So in this little square table for two classes, you would like to see just non-zero numbers on the diagonal, but of course that won't always be the case. So the definitions are given below here. The true positive rate, the top left one, is the sensitivity, and the bottom right one, the true negative rate, is the specificity. Those are very useful, and for many problems, classification problems, you will be more interested in optimizing on one or the other of those. If it's most important to you to get all the positives, to identify all the positives, and you want to have true positives to be large. Maybe you're not as interested in or you want to guard against false positives, so you would look at that rate. Okay, let's go to the next slide. Okay, and that's pretty much the same. There is in the confusion matrix, there is also a misclassification error, which seems like a nice summary method. It's the proportion of samples that were incorrectly classified, so class identified as belonging to a different class. That is, it's only actually accurate if the numbers of samples in each class are balanced, because if there's great disparity in the number of samples in two classes, then you could just say any prediction is going to be that dominant class, and it will give a good misclassification. You'll get a good misclassification error, but it's obviously not good for the samples that do belong to the smaller class. Okay, next slide. So yeah, this is where in all of the classification methods, there is an icon for pulling up the confusion matrix. And it also brings up the confusion table, which the confusion table is perhaps more convenient because actually go to the next slide and I'll show what you get. This is a subset of what you get when you click on that icon. And this was for PLSDA with 2 classes. That on the upper half, you see the confusion matrix results. And in the lower half, it's what we refer to as the confusion table. And that just shows a square box again for the actual class versus predicted class. And in practice, I find this to be maybe the most convenient thing to look at when I've built a new model. I can just look here and see very quickly if the diagonal is, if it's perfect, and the only non-zero numbers will be on the diagonal. In this case, there was one misclassification. But that's a very quick view to get a summary. I think if you're using these a lot, then maybe looking at the confusion matrix numbers will be as helpful to you, but you get to see them both. And this will also show, when you click on that icon, you essentially get to see this information 4 times. You see it as shown here, but you also get to see it shown for cross-validated results, which might be more relevant to you. And also, you see at the top line there, it says prediction using strict threshold, or classification rule using Fred strict. So let's go to the next slide. That brings up, there are actually, so all of the classification methods produce a probability of belonging to each class. We have 2 rules for how the classification is reported. One is called the most probable, and that's simply looking at the most probable class that you get. The other is strict, and that will be a more conservative approach where you will not assign a sample to a class if all of the probabilities for that sample are really small, for example. And so let's just advance and probably go a little faster over the next few slides. If you click on the scores plot in classification methods, this is what you see, something like this. And on the left in the plot controls, you see the different quantities you can look at. Measure, class measured, okay, class pred strict, class pred most probable, and then the for each class, pred indicating whether that class is predicted or not. And some methods allow a sample to belong to more than one class. And then unassigned and multiple. Okay, let's advance. Okay, we can go past that. That's what I was just describing about the 2 rules. And this is a summary of those different quantities you can look at. The class pred most probable, you will always get a most probable, even if they're all the probabilities for a sample of belonging to the different classes are all really small, you'll still get a most probable. And while that's convenient to always have a predicted class, it might not be advisable in that case. And that's why we introduced this strict prediction rule, where basically the rule says that only one class should be predicted, and that the probability has to be greater than 0.5. That threshold can be adjusted by the strict threshold option. Okay, let's go ahead. The predicted member, if you click on that, for each class, it'll basically show a plot of whether that's of samples and whether they belong to that class or not. Misclassified is, again, if you're using the strict rule, if for some reason, either because a sample is predicted to belong to more than one class, or none of its class prediction probabilities were greater than the threshold, then it would be classified as misclassified. Okay, next slide. Okay, and that link at the bottom it describes these in a bit more detail. Okay, that's that. Let's go ahead. Oh, the last thing that I was going to mention is that a common way to view results of binary classifiers is to look at a ROC curve, receiver operator characteristic curve, and that is available in PLSDA, and it sort of gives an overview of how well the model predicts for different settings of the threshold. Every model has, well, a model like these PLSDA models, there is a threshold in the Y predicted where you say a sample is going to belong to class A or B, depending on whether the Y predicted is greater than the threshold or not. So varying that threshold, you can draw up an ROC curve showing how sensitivity and specificity vary for those thresholds. Okay, so over to you then again. I think if you click on the next slide, it's where
Yeah, and I can take this down. The idea behind the hierarchical models can be easily described by thinking about the Airlade data set, but we've got a different data set here where the idea is that if you have one class that seems to separate very easily from others, like let's say this would be a class that would be very easy to separate from the other group. You could build, for example, a PLSDA model and split this guy from everybody else. So I would group these as one class and this is another, and I could split this guy from the entire group. And we use our hierarchical model builder to do this, to develop a full classification system. And that's down under tools. And it's a fun thing. It's a little difficult to learn, but it's actually very powerful. For example, here I develop a rule. I can split into 5 different decisions. For example, I was splitting this into 4 classes, not just the one, or 3 classes versus other. And then there's the otherwise. It says it's an unknown material. So I can develop this by setting up my rules and having a solution. And the solution doesn't have to have a string. It could have a value, an output as well. And we have everything you need to know about the model builder as well. This is really, really powerful. And this is where you can take a lot of control of your classification approach. And so if I'm in the other class, then I can have a rule that says, okay, well, now let's split it into 3 more classes and have an output, and then another. And so this is going to be a harder group to split apart, but these I could split away from them, and I get into this subset here, and now I start having smaller classes, and then another other, and I keep building on down and split things apart. And so in conclusion, we talked about getting started and getting the classes set up in our data set object. And so you have to select then the classes that you'd like to model, combine the classes as necessary, just as I showed in the hierarchical approach. You could combine classes, or as I did with the PLSDA. I use exploratory analysis with principal components analysis to help guide me in those decisions. This is a very important thing to do, is look at your data. There are lots of methods to choose from, and it really is often hard to say a priori which method would work best. So I would suggest that you start with linear techniques and try to interpret your data, for example, PCA or PLSDA, and then you can easily switch between them at the analysis interface to try different ones. Of course, as you get into the nonlinear techniques, there can be lots and lots of metaparameters, and it gets slower. So you can set those up to run and then go have a cup of coffee sometimes. Donald talked about the confusion table, which in and of itself can be confusing, but there are good wikis and good information available to learn about them. And this webinar is being recorded, so you can watch that again to see Donald's descriptions. And the hierarchical idea is that we break hard problems or many multiple class problems into smaller pieces and develop small, simpler models to split them apart in a hierarchical sense. And with that,
We had a
should see if we have questions. Thanks, Scott.
yeah, we had a question here. When using these algorithms such as PLSDA to draw a conclusion on the identity of samples for courtroom litigation or product release, how do you prove the algorithm from a particular software such as PLS Toolbox is accurate?
Validation. You know, I think a lot of people are using these models and they're more focused on fit than they are on prediction. And if you look at our cross-validation webinar, you'll see a lot of harping on that particular idea. But coming in with a separate validation data set that's completely statistically independent from your calibration and the data that was used for cross-validation is probably one of your best ways.
Yeah, I'm coming in late to the party here, but as we say, this is Barry. You don't validate the software, you validate the model. Because there's a lot of ways that the software can work. And the MathWorks actually says this about their software when it's used to do things, for instance, develop a control law to fly an airplane with. You don't validate the software that made the control law, you validate the control law. And you know, I feel that the same way here. The important part is to show that it works on independent data and that it produces the same result during your modeling as it does wherever you've actually implemented it, where you're running it. That's something I feel very strongly about, if you can't tell. Yeah.
I think we all feel that way, Bear.
As part of the answer there too is in the case of a court environment, you really are trying to convince a jury of people who are not statisticians. So having a simple argument like you know, cross-validation or applying to it an independent test data should seem understandable and I guess convincing, as opposed to I don't know, some kind of a more detailed explanation of the method or whatever.
Yeah, I think it's a challenge in general, though, to explain all of these things to laymen. So I guess I would say I feel your pain on that.
Especially with the nonlinear methods, you know, like ANN or something, you know, it it is a bit of a black box as for what it's doing.
A bit? Okay, that's an understatement.
A black box in a black box.
Donald understands it.
Here we add another one. Is there a preferred way of validation when comparing between cross-validation and having an independent set of data?
Is there a preferred way?
Well, maybe like is there which of those two is preferred?
Oh, well, the completely independent test set is validating your model the best. And I really mean statistically independent. It can't be like selecting, if I collect the data on day one and split that into cal and val, that might not actually capture everything that could go on in the future. So what I really want to do is like turn off the machine, make it all completely stopped, start it back up, and redo the whole method, you know, a week or two later, and see if I can validate my data. Validate my model, sorry. Well, we're at the top of the hour. We don't have any other questions. I think we can draw this to a close.
Nope, no more questions.
Excellent. Well, thanks everybody for being here. It's been a pleasure to talk about this stuff. And Donald, I really appreciate all of your input. You had the hard part to do.
Thank you, Neil. Oh, there was a question just came in.
Yeah, does PLS Toolbox automatically transform or code categorical variables before use? If not, is there a recommendation for how best to include categorical data?
If you set up your classes in your data set object, like we were showing earlier, where you set up your class variables over here, and so you create your categorical variable there, then in PLSDA it will create the Y block for you. You know, in all of these techniques, the Y block is created automatically, but it comes from this class information.
And in the actual PLS toolbox, that's the class 2 logical function for those who like to get into that.
Right. And if your spreadsheet, for instance, if your categorical variables are essentially in there as labels, you know, when you bring labels in and you can create a set of classes out of those labels. So, you know, if you've got 10 things with this label and 15 things with that other label, then those become the classes for those things. Hello?
Hello?
Well, I think it's time to wrap it up.
Okay.
Thanks all.
Thank you, everyone.